first of all, thanks Nicole for organizing this webinar so that I can share my research work to all my friends here. Okay, today I'm sharing with all of you my research work on the design techniques for multiple output Mimo antennas, and this is the first part of the talk. And subsequently, I will share with you my research work on the UHF RFID tech antennas. And this will be the second part of my webinar today. Okay, so we straight away move on to the introduction of this Mimo. So of course, fifth generation of our wireless technology, it can offer very massive data rate up to 20 bytes per second. And of course, so, and also a very high capacity hall. And of course, the application of 5G has been spanning from smartphone, drone, Internet of Things, and autonomous driving, and so on, right? There are many places that you are seeing the real applications of 5G today. So, and of course, but 5G, the propagation of 5G signal of the electromagnetic wave can be easily affected by different attenuation from our environment, which can cause significant deterioration, in the 5G communications. The environmental factors includes water vapor, city buildings, storm, and so on and so on. So over here, of course, multi-path, of course, is one of the biggest challenges of this 5G propagation. So in order to overcome this problem, Mimo, the use of multiple antennas at the input and multiple antennas at the output is one of the solutions that can be used to improve the wireless performance. Of course, you can see that the signal can propagate through many paths. This is called multi-path, So that with the engagement of multiple antennas, so that this problem can be overcome quite efficiently. So of course, over the years, there have been different bands that have been explored for this 5G smartphone antenna, So that the antennas that we are discussing today will be particularly used, for this smartphone, this 5G smartphone. Namely the N77, which is covering 3.3 to 4.2 gigahertz, and N78, which is covering from 3.3 to 3.8 gigahertz, as well as N79, which is covering from 4.4 to 5G, So that you can see that since you are employing a couple of antennas, at the input and at the output. So and of course, since you are putting it inside a smartphone, you have to pack all those antennas very close to each other. So because of this, it has to be very small in size and low in profile, So that they can be fit into such a mobile device. So that because you are packing all these antennas very close to each other, so that the placing them very close is unavoidable. So that, but of course, because you are placing all these antennas very close to each other, and it will cause a mutual coupling in between the antennas, and this can cause significant degradation, Because of that, isolation has become a very important problem, A very important technique that is needed. The performance wireless communication system. So you can see that, okay, over here is showing you, two antennas which are excited without any isolation, You can see that, more or less, the EN power from your antenna 1, it can be coupled to your port 2, from your antenna 2 to antenna 2. Here, it's showing you, of course, later on we will elaborate on that, So here, an EBG superstrate of the antenna in order for improving the isolation, So from here you can see that, with the application of this EBG surface, basically this the coupling to port 2, can be effectively mitigated. So okay, now we move on with some literature reviews on those isolation techniques. So okay, so I will start first with the use of orthogonal modes, right? So that to perform this Mimo isolation, there are a lot of techniques that have been proposed in the one of the very popular one is the use of orthogonal modes, right? So it means, right, okay, you are using the orthogonal modes in the antenna, right? Of course, you can see that, for example, this antenna is taken from this reference, which was published in year 2020, right? So that, okay, you have antenna one, you have input one, input two, your antenna two, input one, input two, right? Basically, you have four antennas here with eight ports, right? So you can see that, right? All the antennas, they are packed in such a compact space, right? So that in order to mitigate the coupling, right? So that later on you will see, right? The even and odd mode technique or in phase and out of phase excitation technique will be applied over here. Because, right, over the years, right, there also have been some works on not only for this is on the single band, right? Also for the multiple band. And this paper particularly. So not only that, right? So that just now you also saw that, right? The use of EV structure, which is one type of metal material, was also employed to enhance the isolation in between the two antennas. For example, here, this is taken from this paper, right? And you have antenna one, antenna two. And here, right, on top of it, metal material surface was applied on top. So in order, right, to improve isolation in between the two antennas. Not only that, right, this is showing you another paper, right, which has employed, right, this metal material, right. You can see that this is basically a pitch with a U shape, and of course, right, with this U shape, basically, right, dual band can be excited, right, in each of the antenna. And of course, right, with the application of this, now the pattern here, right, is different, right, from this paper, and it can isolate the two antennas in the two bands effectively. Okay, now we move on to the next one, right? And of course, another type of isolation technique is with the employment of lump elements, right? This is a kind of the filtering effect, right? So that, okay, let's say you have antenna one, antenna two, right? Let's say you have here antenna one, antenna two, antenna four, right? And actually, right, this configuration is taken from this paper, right? So that, right, if you have applied some lump element in between them, right, with a proper calculation, the antenna ports, the coupling in between the antennas can be effectively mitigated. So not only that, right? Not only that, so here, right, it's only using this design here is only using the inductor and capacitor, right? But actually, right, on top of that, right, you can bundle them together, right? Just like designing a filter, right? So that in this paper and this config, right, actually it can do isolation for two bands effectively, right? For this Mimo antenna, right? And this config is taken from. So okay, now we go to design methodology, right? So usually, before we perform the design, right, we will do a bit of literature survey, and after that, right, we will apply the knowledge that we have learned, right, to design the 5G antenna. And after that, right, I think in modern antenna design, it is very crucial to simulate and optimize the antenna configuration, right, with the use of a software, right? For example, CST or HFFS, right? So you build up the electromagnetic model, you do a bit of a simulation or an optimization, right? Before moving to the fabrication of the prototype. So after fabricating the prototype, then, right, you will measure the antenna performance, right, with the use of vector network analyzer, right, which we will go through today. And finally, right, of course, right, for academics, then we will publish the result or we prepare a thesis, right? So that for industry, we have a lot of friends from industry today, right? So that for industry, right, then you can deliver the product to your customer. Okay, here is showing you, right, the simulation space that we are using, right, to simulate our antenna. And of course, right, for my research work here, we are using the CST Microwave Studio to do the simulation and optimization. So here, right, after performing, right, the simulation and optimization, then we go ahead with the fabrication process. Basically, right, so since we have engaged a planar antenna, right, we can use the chemical printed circuit board etching process, right, to see that, right? We use the photoresist method to shape the antenna pattern, to make the antenna patterns on this FR4 PCB, right? And after that, right, we go through we make the PCB through the chemical etching process, right? So that you can see, right, after employing the chemical etching process, so that, right, the antenna pattern, and also at the back here, right, you will see that, right, there's some slot here, right? Actually, this one is functioning as an isolator, right? It will be etched on this slot, right? This isolation structure, right, actually, right, is connected to the ground here on the reverse. Okay, so now here, right, I will go through with you the simulation process, right? So you can see here, right? Okay, here in the simulation, right? First of all, we have built up, right? This is a 4-port antenna, right? You have your antenna 1, antenna 2, antenna 3, and antenna 4, right? Which are connected to a 4 SMA port. So on the reverse side, you have this so-called, right, the unprotruded multi-slot structure, right? Which to the ground plane, right? The isolation for performing the isolation, right? So actually, this antenna structure was proposed in this paper. So okay, now you can see that, right? This is showing you, right, the effect or the electric field intensity for the case of without the UPMS structure and with the UPMA structure. Okay, first of all, on your left hand side, you see that, right, when there is no UPS MS structure, okay, when you are feeding your antenna 1 on, basically the signal is coupled to your antenna 2, right, due to a very significant coupling. You can see even from here, right, the field here, there is a significant coupling in between antenna 1 and antenna 2. So when you are applying, right, this isolator structure, right, okay, now here you can see that, right, when you're exciting your antenna 1, there is no field excited to your antenna 2, right? Of course, right, there will be a little bit of field, right, but it is very little, right? So that you can see that you can see on the reverse side, basically, right, the isolator is working well to isolate the field from propagating to your this fit tube, right? So here is showing you, right, the after the CXT modeling, and we can actually, right, to the some software, let's say AutoCAD, right? And after that, right, we can fabricate this prototype out easily, right, through the PCB etching process. So okay, next, right, we proceed to the this measurement, to this measurement, right? Okay, I move here a bit here, right? So, or actually, in our measurement here, we have we have employed, right, two different types of vector network analyzer. So on your left hand side, we have employed this model, right, which can measure, right, from this a very low frequency up to a 13 point something gigahertz, right? So on our right hand side, we have engaged the BERT VNA, this VN 900 model, right? This one with a 4-port, right? For measuring, right? Because now you can see that, right, we have a 4-port antenna. So for this particularly, right, for this BERT this VNA, right, it can provide 4-port measurement straight away, right? So for this 2-port measurement on the right and side, right, because it has only 2-port measurement, for sure, you have to engage two broadband match, right, PTO match. You can see here, right, so that at any one time, you can only measure any 2 ports at any one time. The other 2 ports, they have to be properly matched using the broadband matches. On the other hand, for this 4-port, right, BERT VNA, right, you do not need to have any matches. You can connect, right, all the 4 ports to this prototype straight away, right? And of course, right, and one good thing about it is that, right, you can straight away it will be straight away sent to this laptop, right? And here, right, you can process the data straight away immediately. Okay, so here is showing you, right, our connection, right, for this 4-port. So later on, right, you will see that, right, we will have another 8-port measurement. Later on, I will show you, right, our design of another 8-port antenna, right. In this case, right, you can still perform 4-ports measurement here, but with the other 4 ports, right, match. So okay, here is showing you, right, our this the comparison So these are your port 1, port 2, port 3, and 4 port, right? And port 4. So okay, here on the left-hand side, you have the simulated and measured result for the reflection coefficient. Here is showing you, right, the S11 and S33. Means that, right? Okay, and over here is showing you, right, the S22. I move this up, right? It's showing you the S22 and S24, right? In principle, the reflection coefficient, they are agreeing with the measurement, right? The measure results are agreeing with the simulation very, very well, right? And of course, right, not only that, right? So here, and you are shown with the couple result, right? So here is showing you, right? So the coupling mechanism in between the port 1 and port 2, right? Which is in S12 and S21, which are shown here, right? Measure over here. And one good thing to mention here is that, right, you can see that, of course, right, the coupling signal is very weak. It can go down even, right, to -40. For both cases, right, both the bird VNA and the rod and short VNA, right, the results are equally good. You can see, right, with a very good resolution, right, for the very weak signal. This is true also for the S34 and S43, right? You can see that, right, when going down to -30 dB, right, the resolution of the measurement, right, is still very, very good. And they are agreeing, right, very well to the simulation. So, and of course, right, this is showing you, right, the coupling measurement for what? For the S14, this is your port 1 and port 4, right? So they're right. So here is showing you the simulated and measurement comparison, right, for this S13 and S24 for all, right? You can see that, right? Particularly, right, for this S31, it can go down to -30 dB, right? And for this S24, right, the coupling in between the port 2 and port 4, right, it can even go down, right, very near to this -45 dB. For both cases, right, all the measure results from with this draw and SWOT and the bird VA, right, both are agreeing very well with the simulation, right, and both are showing very good resolution for the small signal. Okay, here is showing you, sharing with you, right, with another simulation, another Mimo antenna, which has 8 ports, right? So basically, you have 4 antennas here, 1, 2, 3, 3, and 4, right? So each of the antenna is supported, is fed by 2 ports, right? So that here is showing you, right, the feeding scheme, right, which you have this port 1, port 2, port 3, port 4, port 5, port 7, and port 8, right? And this is actually, right, taken from this paper, right? And of course, right, remember in the very beginning, I've told you that, right, this the use of even on-mode, right, and or in-phase or out-phase feeding, right, is one of the very efficient techniques that can be used for to have this isolation. So okay, now, right, we are applying it on the design of this antenna here. So okay, a little bit of theory here, right? So how it is done? You can see that, right? Okay, here is showing you, right, the common mode excitation for each of the antenna, right? So for the common mode, okay, you can see that, right? Okay, this is the current pattern, right, on it. So over here, you have the differential mode. When the antenna is excited in the differential mode, right, you have the current in out of phase, right, as shown here, right? So okay, now, right, where here is showing you when you are exciting, right, the port 1 particularly, you see that, right? Okay, this common mode, when the common mode is excited together with the differential mode, right? So that, right, particularly here, you can see that, right, the current, they are opposite in the direction. So that over here, the current will be cancelled out, right? So it applies the same theory apply also for the port 2. And of course, right, for the port 1 here, right, the current pattern on the port 1 here, they are in the same direction, so that, right, they will be enhanced, right? So that's the reason why here, right? So that, right, no field will be because of the cancellation, so that the port 1, it will be decoupled from port 2. So also for this when port 2 is excited, right? You can see here for the port 2, okay, on here, right, the currents are enhanced, but over here the currents are cancelled. So because of that, so that right, the port 2 will be effectively right decoupled from your port 2, right? So this is showing you, right, this technique is called the current mode cancellation method, right? So such a technique, it has been employed to provide such a good isolation. So again, right, we have fabricated the prototype and perform the measurement, right? So okay, here is showing you, right? So you can see that, right, for the because each of the antenna, there are two ports, right? You can see that, right? We have measured the S11, S22, S23, S44, S45, and so on and so on, right? So all are shown here. For S01, S44, S45, and S8, right? You can see that, right? The simulation is actually, right, agreeing to the both of the measurement very well. Particularly, right, for this bulk VNA, right, you can see that the resolution is very excellent. It's agreeing very well, right, to the rod and SWAT VNA. And for this S22, S23, S66, and S77, right? And again, right, the bird measurement is agreeing very well with the rod and SWAT measurement, right? And both agreeing well to the simulation as well. Okay, and for the coupling measurement, for example, you just now you saw that, right? Your antenna one, there are two ports, right? So that we measure the coupling in between port 1 and port 2, right? So also we measure that for the port 3 and port 4. It means that, right, for the same antenna for the different ports, right? You can see that, right, due to the current cancelling technique, right? So both of them, the isolation, right, in between the two ports, actually, right, is very well. It can go down well below minus 15 dB. And of course, right, for both measurements, they are agreeing with the simulation very well, right? It's showing you, right, this bird VNA, right? But one thing to mention is that, right, to get this data, right, for bird VNA, it has 4 ports, so that, right, it's much faster, right? So that it means that, right, you can obtain the curve for 4 ports at any one time. But for this rod and SWAT VNA, right, that we have employed here, right, the ZVR model, right, it can only obtain any 2 at any one time, right? So, for example, if you want to measure, right, for this antenna, right, you can only measure 2 ports. So the rest of the port, as you can see here, right, you have to use 2, 4, 6 broadband matches, right? Broadband matches, which is a bit of inconvenient, right? Of course, right, but for the bird, right, you only need to use 4 instead of using 6, right? So again, right, for this H21, S43, S65, and X7, right? Again, right, we have the measurement agreeing to the simulation very well. Okay, now here. Okay, now we move to this the cross coupling, right? Okay, I move this panel down, right? So okay, this is measuring the S13. It means that, right, okay, the coupling in between the antenna pair 1 and the antenna pair 2, right? But in between the port 1 and port 3, and also, right, vice versa, right? We want to see the coupling from port 3 to port 1 here, right? So again here, the coupling is controlled well below minus 20 dB, right? And both the bulk VNA and the rod and SWAT VNA, right, they are giving very good measured result, right, as compared to the simulation. And again, right, so that in between, we also measure, right, the port 1 and port 4, and also, right, port 5 to port 8, right, and 8 to 5, which are the corresponding ones, right, in the opposite side. Again, right, they are agreeing quite well, right? Of course, right, this simulation, right, it can go down quite low, right? But of course, right, in measurement, right, both the VNA are giving, right, very good, very similar result. Okay, now here, right, for again for the S23, for the coupling, right, in between the port 2 and port 3, right, again, right, you can see that, right, very good agreement in between the simulation and measurement. And this applies also for the S24, S42, X66, and X86, right, which are the corresponding counterparts in the opposite side. So again, right, so this is showing you again, right, the coupling. For example, this is the couple signal in between the antenna pair 1 and antenna pair 3, right? So again, right, you can see that, right, of course, right, in the simulation, right, you have here, of course, right, in the simulation, because it involves many ports, right, so that, right, we use less resolution, less accuracy, right, in the simulation, so that, right, it can produce this result faster, right, but in the measurement, you can see that, right, both the bird VNA and the rod and soft VNA, right, they have generated, right, very accurate resolution. But for this very weak signal, and this even can go down, right, to minus 40 dB. As well as here, right, you can see that, right, for the X26, right, here, the coupling between the two, right, it can go down nearly to minus 50 dB, right, and the agreement in between the simulation and measurement are quite good, right, and of course, right, you can see that, right, the bird VNA, the bird measure result, right, the measure result for the bird VNA, right, the resolution is excellent. It can go down to a very, very small value, right? Okay, again, right? They're showing you, right, the measurement, the comparison, right, in between the measurement for S17. It means, right, the coupling in between port 1 and port 7, right, which is in the range of minus 30 dB, right? And again, right, both the measurements are showing very good agreement with very good resolution along the whole frequency range. And this apply also, right, for this S27 27, right? It means that the coupling in between port 2 and port 7, right? And so on, right? And the corresponding counterpart. And also, right, for the port 1 and port 8, and the coupling in between port 1 and port 8, right? Which has gone down well below, right? Minus 30 dB. And again, right, you can see that, right, the bird VNA is agreeing with the rod and sword measurement very, very well, right? With very fine resolution. Okay, I think there is this is the final page for my this part 1.